Hi, you're it. So before we start on to today's work, pause the video, answer your retrieval roulette questions. Okay, hopefully they're done. So here are your answers for marking and correcting your answers. Now, 2 weeks ago we started this heat topic, and in that very first lesson we talked a little bit about how the mass of an object will have an effect on how much heat energy affects it. So like what the temperature rise will be for different masses. Now, then, do you remember page 49 I'm on here? We skipped over this experiment. I'm going to try and do that with us today, okay? So if you open your notes at page 49 for me, please, and then be ready to write this stuff in. So there's a few different ways that we can do this experiment. If we look at the title of it, it's an experiment to investigate the time it takes to raise the temperature of different masses by the same amount. So in school, we've done this a couple of different ways in the past. One way we've done it is with a wee beaker of water and a Bunsen burner, and then we have recorded how long it's taken for the water to rise by 10 degrees Celsius, okay? Another way is that we have these aluminium blocks in school and we can use an electrical heater to heat them up, and it's the exact same concept. We just time how long it takes them to the temperature to rise by 10 degrees Celsius, and then we reach some sort of conclusion from our experiment. So I'm going to try at home to do the water version, okay? So I'm going to draw in the apparatus that we would use in school, and then I'll tell you how I'm adapting it for home. Okay, so this is the apparatus that we would use. So if you pause the video and get that drawn in for me. Okay, so hopefully you have that drawn in, and I will talk you through it now. So remember, we're investigating how long it takes to raise the temperature of different masses of something. That something's going to be water by the same amount. So we're going to raise the temperature of water by 10 degrees Celsius. Okay, different masses. Water has a density of 1 gram per centimetre cubed. So that means that if we have 1 centimetre cubed of water, it will have a mass of 1 gram, okay? And I'm going to use that fact for varying the masses of my water. I'm just going to use different amounts of water, and because I know how to convert between centimetres cubed and grams, then it means I'm going to know the mass of that water. Hopefully that made sense. So what we're going to do is use our measuring cylinder. Sometimes these are called graduated cylinders, to measure out different volumes of water, and obviously the different volumes of water are going to have different masses. We will put that into a beaker in school with a thermometer in it and record the starting temperature of the water. The beaker is then set on a wire gauze, which is on top of a tripod, so that a Bunsen burner can be put in underneath to heat up the water. As soon as that Bunsen burner is put in underneath, then we would start our stopwatch and just keep watching the wee thermometer and see how long it takes for the temperature to rise by 10 degrees Celsius. Okay, and then we would do that for various different volumes of water, which would be various different masses of water. Hopefully that made sense. So I was thinking about it, and I can pretty much do this at home. I can use a measuring jug instead of a measuring cylinder. I don't have a Bunsen burner and everything at home, but I could just use a saucepan on my cooker. So that's how we are going to do this today, right? So hopefully you've got that drawn down. I'm going to go through a method here to show all the different steps that we have to carry out in our experiment. So our first step, measure out 200 millilitres of water using the measuring cylinder. If we were doing this in school, the volumes of water that we would be using would be much smaller. I'm just thinking about a saucepan, and I don't want to have a wee tiny wee amount in the bottom of it. So we'll see how we get on with these sizes. Okay, our second step, pour the water into a beaker and record the initial, which is just a fancy word for starting, so the initial temperature of the water using a thermometer. I want to just point out to you here that whenever we're writing methods, we always try and say what we're doing and how we're doing it. So we would always say like what we use to carry out the procedure, right? Okay, step 3, start the stopwatch, and at the same time place the Bunsen under the beaker. I suppose I should have said Bunsen burner there. bad habit. Okay, got a bit carried away there and I've done the rest of the steps. So step 4, stop the stopwatch when the temperature of the water has risen by 10 degrees Celsius. Then record that time and then repeat all of those steps for 300 milliliters, 400 milliliters, 500 milliliters, 600 milliliters of water. Okay, so pause, get those written in for me, please. Now, we'll have to think about precautions that we would take to make sure this is a fair test. And if you remember from like the bouncy ball experiment we did earlier on in the year, we would have talked about what a fair test is in that. And if something's a fair test, the only thing you can change is the factor that you're investigating. So for us, we're changing the mass of the water or the amount of the water. And then we're seeing how long it takes to heat up by 10 degrees. So that means everything else has to be exactly the same. So for this setup, it would be having your Bunsen burner on the same setting. So my ring and my hob, I'm going to have that on the same setting. But just basically everything else, same size beaker every time, everything has to be exactly the same. Otherwise, there's some other factor that might affect your results other than the mass of the water, and then you don't know why it's happened like that. Okay, so here's mine. If you've thought of any others, put them in too. So the Bunsen burner should be on the same setting throughout the whole experiment. The same size beaker should be used throughout, and it should be made of the same material. Now, in an ideal world, you would use the exact same beaker every single time, but you would need to make sure you cooled it in between. Otherwise, that's going to affect like your heat source, because if you don't allow your beaker to cool down in between, then that is like a wee extra heat supply that the water's going to be getting, and it's going to affect your results. So whenever I'm doing this, I'll probably just run my saucepan underneath the cold water for a wee while to take any heat out of it before I start on the next one. And then the starting temperature of the water should be kept the same each time. Now there's bound to be some that I have forgotten there, so if you have thought of any others, make sure you write them in. So over on page 50, we are going to draw out our results table. So in our results table, we always have to think, right, well, what are we going to be measuring? And make sure we have a little space for everything and say what units that we're measuring it in. Okay, so I will start here and then I'll talk you through it. Okay, so here's my results table. So our first column is the volume of water, because that's how I'm going to be measuring it in milliliters. If you put your unit after a little slash at the top of your table, then that means that every number in this column is in that unit, and you then don't put the unit on your numbers within the table. Okay. Now my next column I've put in is mass, because I know that whatever my volume is in milliliters, that's how many grams of water I'm going to have. So if my volume of water is 200, my mass is going to be 200 grams. So I can fill the rest of them in now. Okay. Now, next one then is the initial temperature measured in degrees Celsius, and then the final temperature measured in degrees Celsius. The reason that I'm including this column is so that it reminds me while I'm doing the experiment what temperature I'm looking out for, because it can be easy to forget that. So whatever this is, my final temperature is just this one plus 10, remember. And then the time taken, and that's going to be measured in seconds. Okay, so you get that written down, and I'm going to go and do the experiment. Okay, so here I am. I've got my water in my measuring jug, recorded the starting temperature. That's the wee, like a wee digital thermometer I have there in my saucepan, and I'm just using the stopwatch on my watch to record the time for the temperature to go up by 10. And if you see, you can see me getting down eye level for reading off the volumes. If you don't, you're likely to make a wee mistake and read it wrong. So hopefully you can see me doing that. Right, so here's the results. I'm going to say I don't think I carried that out perfectly. And you can probably tell that because my increase in time for everyone isn't consistent. Okay, so things that maybe went wrong. I don't know if you can tell in that wee video, but I made sure to always get down eye level for checking the volume, but my measuring cylinders aren't the most precise things in the world, so, or my measuring jugs I should say, so it's likely some of my volumes were a bit out. And if you could tell in that, I was struggling with starting my stopwatch and stopping it and holding everything at the same time. So there's probably a couple of dodgy results. Also, my cooker is not the most consistent thing in the world. So anyway, here's our results. Pause, get those copied in for me, please. Now we're going to write a little conclusion as well. Remember, the aim of this experiment was to investigate the time it takes to raise the temperature of different masses by the same amount. So we were raising the temperature by 10 degrees Celsius, and hopefully you can see from this table that as the mass of the water increases, the time taken for the temperature to rise by 10 degrees also increases. Okay, in like if we were doing this a bit better, we would probably plot a graph of our results. I'm not sure I trust my results enough to bother with a graph, but we should end up with a nice straight line graph if we had better results and if we were to plot it. So anyway, let's get this conclusion done. Okay, so here's our conclusion. As the mass of the water increases, the time taken for the temperature to rise by 10 degrees Celsius also increases. Then I added on here at the bottom, bigger masses take longer to heat than smaller masses, but I've added in here, which is important, that's when the heat source is the same, because obviously if you had a big mass but you had a really high energy heat supply, that's going to heat up quicker than if you have a small mass and like a really rubbish heat supply. Do you know what I mean? So as long as it's a fair test, the bigger masses will take longer to heat than the smaller masses. So if you turn over to 53 for me, please, we're sort of going to do like it's like a lesson of two halves here, nearly year 8. So last week we started talking about how conduction, which remember is the transfer of heat through solid materials, how well that happens depends on the type of material. So some materials are conductors, and that means they allow heat energy to transfer through them quickly. Some materials are thermal insulators, and that means that they don't allow the heat energy to transfer through them very quickly. It still does transfer, but it just doesn't happen very well. Then we looked at an experiment to investigate the rate of heat transfer through different metals. Do you remember the one with the water trough? And you had written out all the instructions for it. What I want us to look at now is just like another version of that experiment. Okay, so it's on page 53. Now we've got this little bit here, and it is an insulating hoop or ring. I'll go for ring. Okay, so this is just made out of an insulator, so the heat energy won't really be transferring along it. Then you can see here we've got 4 different metals, and they all have the exact same dimensions. Now this wee diagram shows this sitting upside down, and the reason for that is that we add on a little drawing pin. Now I have a feeling I'm going to be linking here Mr. Ross's video again of doing this experiment. I think he maybe uses wee screws in his, but I normally do it with drawing pins. So drawing pin. And we attach that on with wax. Do you remember last week the one was with like grease, like a Vaseline or something? This is attached on with candle wax. Then we place a Bunsen burner. So I'm going to draw in a little Bunsen burner. Don't know why I'm using red, I don't like it. Underneath in the center. And oh, this is terribly out of scale. And this would be sitting on a tripod. Okay, I apologize for the scale of this diagram, but we tripod. And then this is our Bunsen burner. Okay, now it's the exact same principle. We put our heat source right in the middle here, and then the heat energy is going to conduct along these metal bars, and whenever it reaches the end, it'll melt the candle wax and the drawing pin will fall off. So all we have to do is look for the drawing pins falling off, and we'll see which material is the best conductor. So again, we're going to have to write out our method for that, so let's do that now. Just before we do, actually, I realised I wanted to add in another couple of wee extra things here. So instead of just drawing pin, stuck on with wax. And then I forgot to label the metal strips as well. So if you label those for me, please, year 8. Okay, so step 1, drop 3 drops of candle wax into the dimple in one of the metal strips. I think I forgot to mention that they were there. There's like a wee dimple in the end of it for doing this. And immediately place a drawing pin in the wax. Pause, get that one written down, thank you. Step 2, repeat step 1 with the other 3 metal strips. So now we're at the stage where we've got a drawing pin in each of the metal strips. Step 3, turn the apparatus upside down and place on a tripod. Step 4, place the Bunsen burner under the apparatus in the centre and start a stopwatch. Get it down. And then step 5, record the time taken for each drawing pin to fall. Now, I haven't left very much room on my page, but do you know what? There's room for a wee tiny results table just up here. Okay, so you're going to record the different metals and then the time taken. Okay, so I'm going to link Mr. Ross's video here. If you click on it and watch it and then record the results down here for me, please. Okay, and then that is us. I'll see you next week. Bye.